On behalf of Trasna, I am Sumaya Banerjee, with Innovations in Charge and Senior Vice President, Trasna Solutions. So today we'll be discussing briefly but technically a topic which is very important for the relation of logistic and transportations. You can see my title, Smart Traceability of Logistic on Move, and we are trying to show our machine learning initiatives, but broadly we'll be trying to show how the machine learning can be deployed with Trustna's roadmap, specifically the design or system design on chip. So before going to anything else, I will try to briefly introduce Trustna branding. Trasna is basically a branded, you can say, future of IoT. Already, this slogan has been very much popularized in the industrial domain. And but Trasna is very much smart in design, and they believe on the intelligent and secure design and sleek design, but everything on system on chip. So today we'll be discussing also these parts, that how Trasna is going to develop and show you the new innovation on the transportation and logistic without less interaction with the cloud. So going to the real roadmap of the present use case, which I'll be describing today, that I can again go back to the screen, leveraging IoT enabled sensors and tiny machine learning on edge. And the target use case is enhancing monitoring of perishable goods. So all we know that whenever we transport the foods items or delivery items, there are tendency and chances and probability that the goods can be perishable during the matter of time, during the matter of transportations, climatic change, etc. So in terms of predicting those kind of perishable goods, and in terms of monitoring the health of the goods, we are trying to use machine learning. Now the question is that the importance of traceability and machine learning is one of the aspect, but the most challenging part is that we cannot track these kind of parameters with only one type of sensors and one type of devices. That means we have plenty of devices, plenty of sensors which can orchestrate or which can help us to predict these kind of use cases or this kind of approach intelligently and with machine learning initiatives. So the question is that we will be giving this agenda, that we will discuss the various types of sensors which we'll be using, and we'll also show that how Trasna will show that tiny machine learning algorithm. I will describe you in brief why it is tiny, because we have already mentioned that we will be having a less cloud interaction. Will be everything will be doing on the hardware on the chip to predict this kind of perishable goods, and some example of the proposed innovations which we are describing here. So before introducing this topic, we'll try to navigate or introspect the importance of monitoring and the current challenges. So, of course, the importance is that how we can ensure the quality and safety of perishable goods, and then how to minimize the spoilage and losses by timely detection of deviations from optimal conditions. That is one of our targets, so that after the transportation and the post transportation phase, there will be no complaint from the customers. And the challenge is that we have temperature fluctuations, as I told you, climatic validations and variations, then humidity variations, vibrations, then the exposure of light and sunlight, especially for the warm countries like India or Asian stuff, then risk of degradation, spoiling, and reduced shelf life, and then edge device requirement, because I have already mentioned that we will be trying to talk less interaction with the cloud. We'll be concentrating on the edge devices much, so there should be less power, limited bandwidth. These are all challenges we'll be facing, and we'll be solving these challenges step by step. So we'll be developing and designing a high level architecture which will be based on machine learning. So let me just tell you brief what is tiny machine learning. Conventional AI and machine learning deploys cloud in a broader way. So we will just train from the environmental data, and we'll try to give the inferences and decision based on the training parts. And this training part broadly happens on the cloud and the user interaction. But here we are trying to leverage these benefits of cloud and try to introduce some benefits how we are going to use machine learning on the devices. That's why we are call it tiny machine learning. Tiny means small. So will not be deploying, or we are trying to make less deployment with the cloud interactions. So if you see my high level description diagram, that we have some kind of edge IoT here, and edge IoT gets the data from the sensors on the board of the vehicle. Data is transmitted to a microcontroller. This is our kernel or nucleus of our design, and this microcontroller turns on the tiny machine learning algorithms which Trasna is developing. And there are two phases here, what is called prediction and what is called training. So we will be having a kind of training algorithm with two algorithms like support vector machine and decision tree. These are conventional algorithms, but for Trasna initiatives we are trying to modify it in terms of our memory, in terms of our power consumption, in terms of our bandwidth, etc. And then after getting a good training and after getting a good alert of prediction, we'll give the detection of the spoilage and try to give an user notification or alert message to the clients and users at the end of the sessions of these kind of detections. So this is our high level diagram. Based on this diagram, we are trying to leverage what kind of sensors we will be using. So if you can see the list of the sensors, we first categorize the temperature sensors, then we'll be going to the humidity sensors, vibration sensor, light sensor, and GPS sensors. Each and every sensors are having their own features, own specializations, and you cannot avoid any kind of sensors for these kind of predictions. And I'll be telling that what are the challenges we'll be facing or we are facing right now to synchronize all these different kind of sensors from the different manufacturers and different developers. So if you see that how we are going to optimize this kind of activities in terms of design, as I told that Trasna is very much known for the smart design and secure design itself. So we are going to have these kind of divisions. So if you can see from my left hand side, we are trying to introduce MCU with kind of special instructions because we will be deploying tiny machine learning. We are not using the conventional architecture of any normal algorithms. Then we'll be having some kind of DSPs because we have to use some serial instruction and multi-device strategies that I will tell you that why. And then we also combine FPGAs, field programming gate arrays, to introduce some reconfigurable hardware. If somewhere down the line our method and our hardware will fail, then this will create a kind of backup methodology. Then we are trying to finalize a neural network and ASIC, application specific integrated circuits. So the journey is from the general purpose to the specialized ASIC purpose. This is our goal, that we are trying to develop some kind of tiny machine learning accelerator to support the device. Then tiny machine learning system integration, as I already mentioned, that most of the big challenges we are facing should be the power consumption, because normally each and every device, they're having a less power consumption activities and data parameters, and here the challenges are much more higher, as there are plenty of vendors associated with different type of sensors. So it is not one sensor manufacturer, there are plenty of manufacturers, and we have to follow a kind of data sheet. So normally in our algorithm, in our tiny machine learning model, we are trying to leverage 100 milliampere power for each and every component of the devices. So if as a total, if you have five or six component of devices, it should be 600 milliampere, something like that. So this is a rough kind of estimation where tiny machine learning can deploy the minimum or less power on chip whenever you are trying to train a model from the data. And all the data comes from the sensors or different devices which have been combined and orchestrated on the transportation system. So if you see the list of the categories of the tiny machine learning, that is based on the sensors data intelligence, because until and unless we get a good data features from all those sensors, we cannot train our models. So we have some motion sensors, we have some acoustic, touch screens, then rotation sensors, environmental sensors, and biometric sensors, and force sensors. These sensor definitions and the sensor definition which I showed you earlier has a little bit difference. The difference is very simple, because here we are trying to specify the tiny machine learning architecture. Previously, what we have showed, that was the list of the sensors which will be orchestrated or which will be populated totally on the system. So this is much more specific, that what the sensor data intelligence will do for the tiny machine learning architecture. Now, to do this thing, we have two components with us. One is the hardware part, another is the software part. Hardware part for the tiny machine learning on the chip for Trasna initiatives. We have combined the heterogeneity because there are much more vendors, or plenty of number of vendors associated with this. Then we have resource constraints. Already I mentioned the power consumption, limited bandwidth, and scalability. Then we cannot expect that every hardware component should follow every required or adequate libraries which will be required to run our algorithm. So of course there should be some missing libraries, and we have a limited operating system support. Please remember that we are talking about devices, we are not talking about the cloud. So we cannot expect all the kind of operating system support which are expected in the cloud, but not on the devices. So therefore we are trying to introduce TF Lite Micro, which is called TensorFlow Lite Micro. This is available in the market, but we need to modify and we need to customize according to our own need. So normally they are hardware agnostic, and there are minimum memory overload, and actually this kind of light architecture will support your model. So this you can see actual story of the machine learning, and this is basically to optimize our memory models, and this is too much on the hardware and device size or on the board size. So TF Lite Micro is already equipped all these features. We are not going to introduce any of the features, but of course we have to modify these features according to our requirement. That I will show right now. So right now we are having these kind of functions. If you are having some kind of background of AI and machine learning, so we must know that these are the activation functions which are really required to train our model. So any kind of neural networks, we need ReLU, we need sigmoid, tan hyperbolic, and Swiss functions. So these kind of functions always having a problem that they are trying to consume much more power. That's why Trasna is trying to develop a hardware neural network, which is a new in the market. And I can show you that hardware neural network is a very simple circuits. You have a summation amplifier, you have an activation systems with power supplies, and we have a operational amplifiers, op amp. So based on these combinations, we'll try to simulate a hardware neural network on chip, which will consume less power. So of course, it is challenging to define and develop such kind of hardware neural network with limited latency and propagation delay. So each and every component, there is no cloud, each and every component should be connected in such a way there should be less latency, so that your training and your prediction should be synchronized at the end of the session. So but all these kind of things should be supported by this activation function. That is the target, so that all the activation function which are deployable in the cloud should be exactly simulated on the hardware. Based on this, we have also found that from the Trasna that we need to design a slick memory architecture. And I am showing you that the memory allocation strategy in design, why we will care for the memory, because we have a memory limit, and I already mentioned that we don't have cloud, so we need to make step by step or batch wise memory training, and we cannot have the luxury to train the entire data features to run our model. So we need to make some kind of fragmentations. But what happens that I already mentioned that the normal operating system which are available with the devices or which will support the device on the system should have a minimum conventional features. So Trasna will develop the adaptive backend which will resolve the issues. That means that if there is lack of operating system support on the chip or on the device side for the transportation system, for the transportation sensors, Trasna's initiative with the adaptive backend can resolve this issue of the fragmentations, so that each and every time whenever we are trying to design something which will be adaptable and will support the design architecture without with minimum support of the operating system from the manufacturers. So I'm just showing a snap of the Trasna strategies for the edge. You can see in a nutshell, this is a typical research paper which has been published in 2019. We are referring this that we are trying to make a kind of convolutional network. With convolution is the heart of any kind of machine learning algorithms. So we are trying to make a matrix multiplications. We are trying to make a weight stationary systolic arrays. And remember, all these algorithms are being operated and orchestrated on the device, on the chip, not on the cloud. So this array architecture, this matrix multiplications, and these input channels and the filter combination will give you the tiny machine learning power on the edge. And then normally, why we are trying to do this? Because Rasna is initiating a bridge between interpreter and compiler. Here is a question that now comes on the software side. Software side has the two part here. One is the Python. Python is essential because we will be having some kind of standard machine learning algorithm, but we have the devices. So that means we need assembly language as well. So we need C++. So we need to initiate a bridge between the interpreter and the compiler. Python is the interpreter and C++ is the compiler. So we need to make a kind of interface and bridge so that whenever we switch from the interpreter to compiler, there should be no jerk, there should be no latency at the same time. So this is depending on the memory. That's why we are trying to design a smart and the slick memory. And the TFL micro, that is the TensorFlow Lite micro, that will solve the purpose because we are trying to customize. So customize means that if we are trying to run a long running application for the transportation network, it will not fail due to the fragmentation. So we need to fragment our memory. We need to design our memory in such a way so that every features and every data site should be supported, but we should make a kind of contiguous memory allocation so that nothing should be missed out. And I mentioned that there is an interpreter and there is a compiler, so we need to interface this in a good synchronous way. So mentioning this fact, always having a question that what is the cost. So this is a kind of clear budget that we have a limited amount of waste facility, we have a limited amount of latency and power consumption. So our framework should have less dependency on waste, rather more dependency on our adaptive backend. So based on this architecture, we are trying
Sonia,
yeah.
I'm sorry, you are over. You have 1 minute to finish.
Yeah.
Sorry
So
for
I'll
that.
finish. So
Thank you.
just trying to show you that we are having a support vector machine on chip. These are the two algorithms we will be designing, and one also will be a decision tree. So support vector machine will give you a classification between the base goods and the perishable goods, and the decision tree will give you a kind of alert message to the customer at the end of the sessions. So we are trying to design that what are the challenges between the power, memory, and the form factor. These are the three things we will be keeping in mind. And we are trying to give the takeaway like this, that we are going for the hardware and software co-design. This is a co-design systems, and we'll try to support especially the 128-bit RISC, and we are trying to frame all the existing software or multiple domain like PyTorch, TF-Lite, and TensorFlow with our smart and slick design of Krasna. Thank you so much. So if you have
Thank
any
you.
question, you can visit
Thank
us.
you, Sonia. Yeah, I have in the chat, there are two questions for
Yeah.
you. The first one, what kind of hardware and software required to perform such ML feature?
Machine learning, I mean, the software part is simple, that we should adopt the tiny machine learning. It should give a kind of existing software, like as I mentioned, the TensorFlow Lite micro, which is available from in the market as an open source. But those kind of open source cannot give you the whole flexibility to support your environment, to support your use case. And for the hardware part, I already mentioned that you cannot get all the sensors to be plugged in with your requirement. So we are trying to design a hardware neural network which will be comprising of a operational amplifiers and the summation circuits and the summation amplifiers and the power supplies, so that all the essential features which are required to perform for the machine learning algorithms should be simulated on the devices. And you must remember that we have plenty of sensors available in the market. So all the sensors are having different data sheets, different data features, power consumption activities, etc. So we cannot synchronize, or we cannot say there is a kind of ready-made solution in the market in terms of hardware. So both hardware and software, we need co-design. That is the essential part of it.
I mean, if I am a designer, if the
Yeah.
designer came from or somebody who wanted to start now project, what kind of MCU, what kind of power, what kind of memory size I will need to perform such ML, tiny ML software?
Yeah. So first of all,
I think the question is more around what kind of resources, hardware resources, I need to have to run such kind of application.
So first of all, we should concentrate on this very sleek design that we are trying to make a kind of microcontrollers, and standard microcontrollers which is available in the market. Power supply should be 100 milliampere. This is our standard 100 milliampere power supply. So if you are increasing number of circuits, if you are increasing number of components, the power supply will increase accordingly. But as I mentioned, that we are using a very light micro operating system, and which is our in our control, so that we should not increase the power consumption for each and every circuits. This is the first answer, that these are the resources are required. And secondly, if you are talking about the category and the section of the microcontroller, this still to be explored, that what kind of specific microcontroller circuit should be adaptable and should be very much synchronized with our use case, that we are trying to answer very soon. But all the other components which I am showing, especially this component, I am showing you again. Sorry. So this is the component part. This is the part that I am showing, that how the 1 milliwatt embedded chip on the low fidelity machine learning model can be developed. And also these kind of circuits, these components are standard components. We can take any components, any registers from this, and we can create a design, smart design for our own. Remember these three parts: summation, activation, and weighting. This is the heart of AI system, heart of machine learning. So each and every machine learning algorithms will having these three components, and we are trying to design a hardware neural network to combine all these components on the ready-made solution.
Thank you, Sumia. It's clear. I think it's clear. Thank you so much. This will be, I guess, the next generation of intelligent hardware and software component embedding such kind of tiny machine learning. Thank you so much.
Thank you.
Let me now